hopefully you've had a chance to try this practice problem. If not, just pause this video and give it a try first and watch the solution after that. So we need to calculate the enthalpy of vaporization for dichloromethane, and we have just a little bit of information. We know the vapor pressure of the dichloromethane at two different temperatures. And so this is going to be our, this first line here, the 100 millimeters of mercury at negative 6.3 Celsius. We're going to call this P1, which is going to make this T1. And then we'll call the second data point P2 and T2. I'm going to need to convert these degree Celsius temperatures into Kelvin. We always work in Kelvin typically in chemistry to make sure that we're not using negative or zero values. That zero, if it was 0 degrees Celsius, would be really hard to use algebraically. So first we can do that really quick here. So our temperature conversions are just adding 273 or 273.15, whichever you prefer. So for our T1, it's going to be equal to 273 plus our negative 6.3. And that's going to give us a value that is 266.7 Kelvin. And our T2 is going to be equal to that 273 plus our 24.1 degrees Celsius that we have. And that's going to give us a value of 297.1. Okay, so I'll use those for my temperatures for my T1 and my T2 rather than the values that were given. And what I'm going to do with them is I'm just going to plug them into our Clausius-Clapeyron equation that I've written out right here. And that's basically it. So let's go ahead and do that. So I'll do this down here. So I'll have the natural log of my second pressure over my first pressure. So that's going to be my 400 millimeters of mercury, all divided by my 100 millimeters of mercury. Forgot the H. All right. So that's then going to be equal to the negative value of the enthalpy of my vaporization divided by R. And R is going to be not 0.0826 or 66.4, but 8.314, yeah, joules per moles Kelvin. And I'm going to multiply that by 1 over my second temperature minus 1 over my first temperature. So that's going to be 1 over my 297.1 Kelvin minus my 1 over 266 point Kelvin. And typically getting to this point is pretty straightforward for students. Plugging it into the calculator is a little bit less so. So I highly recommend just taking a moment to practice solving this out and using your calculator and making sure you're feeling really comfortable with it. So what I got, so as you're kind of playing around with that, just if you need a double point to double check, for just this portion of the calculation where I'm doing the inverse temperatures subtracted from one another, I got a value of about negative 0.00038366. And for this natural log of 400 divided by 100, I got about 1.386. So solving this, I'm going to calculate a enthalpy of vaporization that was equal to about 30,000, 30041 joules per mole. And that joules per mole unit is coming from this R value right here. So it's not going to be in kilojoules. If I wanted to convert it into kilojoules, I definitely could. Instead, then it would be 30.041 kilojoules per mole. Whatever you prefer.